Breaking ground, NASA's 2025 moon landing mission involving over 1,500 engineers and scientists. NASA is on the brink of an ambitious lunar exploration initiative aiming to carry out multiple missions to the moon by 2025 as part of its Artemis program. This groundbreaking endeavor is set to involve over 1,500 engineers and scientists who will focus on developing the technologies and systems necessary for sustainable lunar exploration and preparation for future missions to Mars. Key missions and technologies. Blue Ghost Mission 1. Scheduled to launch on January 15, 2025 aboard a SpaceX Falcon 9 rocket, the Blue Ghost Mission 1 is a pivotal part of NASA's plans. This mission aims to enhance lunar science and technology, primarily focusing on the study of lunar regolith, commonly known as moon dust. The mission will test two critical technologies, the electrodynamic dust shield EDS and the stereo camera for lunar plume surface studies SALPSS. Electrodynamic dust shield EDS. This innovative technology employs electric fields to repel and prevent dust accumulation on surfaces, which is crucial for maintaining the functionality of lunar landers and other equipment. Stereo camera for lunar plume surface studies SALPSS. This camera will analyze how rocket plumes interact with lunar regolith during landings, providing insights that could help in predicting regolith erosion. An important consideration is heavier payloads are sent to the moon. The target landing date for this mission is set for March 2, 2025 in the Mare Crisium Basin, a large dark basaltic plain on the near side of the moon. Artemis 2 and 3 missions. Following the Blue Ghost mission, NASA is gearing up for the Artemis 2 and 3 missions. Artemis 2, targeted for September 2025, this mission will represent the first crewed flight test around the moon utilizing the Orion spacecraft. It will be a crucial step in ensuring the safety and viability of crewed missions. Artemis 3, planned for September 2026, this mission aims to land astronauts at the lunar South Pole, marking a historic moment as it will be the first time humans set foot in that region of the moon. These missions are critical to establishing a long-term human presence on the moon and will lay the groundwork for future exploration of Mars. Common themes across sources. 1. Lunar dust mitigation. A significant challenge highlighted across various reports is the issue of lunar dust, which has historically impeded mission success. The development of dust mitigation technologies is seen as essential for both robotic and crewed lunar missions. 2. Interconnectedness of lunar and Mars exploration. NASA's efforts to study lunar regolith are not just about the moon. The insights gained will be instrumental for future Mars missions as both bodies face similar challenges regarding dust and surface interactions. 3. Safety prioritization. Ensuring the safety of astronauts is a recurring theme. The adjustments in the Artemis 2 schedule reflect a commitment to resolving technical challenges to ensure crew safety before launching any missions. Differences between sources. Technological focus. Some sources emphasize the technological innovations being tested in the Blue Ghost Mission 1, while others delve deeper into the broader implications of the Artemis program for human space exploration. Mission timelines. Specific timelines for the Artemis missions are provided in some reports, while others focus more on the immediate outcomes expected from the Blue Ghost Mission 1. Timeline of events. January 15, 2025, launch of Blue Ghost Mission 1 from Kennedy Space Center. March 2, 2025, target landing date for Blue Ghost Mission 1 on the Moon. September 2025, scheduled launch of Artemis 2, the first crewed mission around the Moon. September 2026, Artemis 3 aims to land astronauts on the lunar South Pole. 2028, Artemis 4 is planned as the first mission to establish a gateway lunar space station. Conclusion. Through these coordinated missions, NASA aims to significantly enhance its technological capabilities for lunar exploration while laying the groundwork for future human expeditions to Mars and beyond. The collaboration between various agencies and international partners underscores a unified commitment to exploring the cosmos and advancing human understanding of our place in the solar system. NASA's Artemis program represents a comprehensive approach to space exploration focusing on sustainable practices and safety, ensuring that as humanity reaches for the stars we do so with caution and foresight. With over 1,500 engineers and scientists involved, the program embodies a collective effort to break new ground in our exploration of the Moon and beyond. The content presents an array of counterintuitive information regarding NASA's upcoming moon landing missions, particularly the Artemis program and the Blue Ghost Mission 1. Here are the key counterintuitive points identified. 1. Safety over speed. While there is often a perception in space exploration that missions are rushed to beat competitors or maintain prestige, NASA's approach is notably different. The adjustments to the schedules for Artemis 2 and 3 emphasize that safety is the top priority, requiring additional time to troubleshoot technical issues. This reflects a paradigm shift where thorough testing and safety protocols take precedence over ambitious timelines. 2. Interconnectedness of lunar and Martian missions. It may seem logical that lunar exploration stands alone as a distinct endeavor, however, the information highlights that technologies developed for lunar dust mitigation directly benefit Mars missions. This suggests that advancements in one area can have broader implications, countering the assumption that missions to different celestial bodies operate in isolation. 3. Dust as a core challenge. One might assume that the primary focus of lunar exploration would be on human habitats or resource extraction. However, the content emphasizes lunar dust as a critical challenge influencing various mission aspects, from astronaut safety to technology development. This highlights that even fundamental environmental factors can fundamentally shape mission design and execution. For commercial partnerships, the narrative often paints NASA as a self-reliant agency capable of executing missions independently, yet the reliance on commercial partners like SpaceX and Blue Origin reveals a shift towards collaboration. This outsourcing of certain mission components shows that even major government space initiatives depend significantly on private sector innovations, which could be unexpected for traditionalists who view space exploration as a government-dominated field. 5. Technological focus on regolith. The emphasis on understanding lunar regolith's behavior and developing technologies to address dust challenges may come as a surprise. Instead of focusing primarily on human life support systems and habitats, the mission prioritizes mitigating the effects of lunar dust, illustrating that foundational challenges often require attention before more complex issues can be resolved. 6. Scientific exploration versus human presence. The content suggests that scientific exploration is not merely a precursor to human presence but is intricately connected with it. The missions aim to establish a sustainable human presence on the Moon while simultaneously advancing scientific understanding. This dual focus contrasts with the common notion that human exploration and scientific inquiry are separate goals. 7. Global collaboration. There is a counterintuitive aspect regarding the expectation of nationalistic competition in space exploration. Instead, NASA emphasizes global partnerships and collaboration, seeking to unite various countries in the ambitious goal of lunar exploration. This reflects a shift from a competitive to a cooperative approach in space exploration. 8. Technological readiness and delay. The expectation is often that advanced technology is ready for deployment. However, the ongoing adjustments to schedules due to the need for further testing of life support systems and other technologies show that readiness is more complex than anticipated. This underscores a reality where technological readiness is an evolving target influenced by ongoing discoveries and challenges. 9. A focus on long-term goals. The immediate missions may seem like the focus, yet the content reveals a long-term vision for sustained lunar exploration and eventual Mars missions. This perspective suggests that short-term setbacks or delays are acceptable in the broader context of achieving a more ambitious goal, countering the expectation that immediate success is the only measure of a mission's value. 10. Public perception of space missions. Finally, there is a counterintuitive element in how public perception might view space missions as purely scientific endeavors. The emphasis on technological demonstrations and dust mitigation challenges reveals the often overlooked engineering and logistical hurdles that underlie successful space exploration, suggesting that a greater understanding of these aspects is crucial for appreciating the complexity of NASA's missions. These counterintuitive elements highlight the nuanced realities of modern space exploration, illustrating that while the goals may be monumental, the approaches and challenges are multifaceted and often go against conventional expectations. The report on NASA's 2025 moon landing mission, part of the Artemis program, outlines the significant collaborative efforts involving over 1,500 engineers and scientists. While much of the report highlights major missions and technologies, several nuanced details may easily be overlooked but are crucial for understanding the broader implications of this initiative. 1. Lunar dust mitigation as a central challenge. One of the critical themes across the report is the challenge posed by lunar dust. Despite the historical data from Apollo missions, the persistent issue of lunar regolith, a fine abrasive powder that clings to surfaces, remains one of the most significant hurdles in lunar exploration. The electrodynamic dust shield EDS and the stereo camera for lunar plume surface studies scalps are pivotal technologies being developed to tackle this issue. Significance. The focus on dust mitigation is significant because it directly impacts astronaut safety and the longevity of equipment. Dust can degrade life support systems, damage spacecraft, and create health risks for astronauts. Understanding and addressing this challenge not only enhances the feasibility of lunar missions but also informs future Mars explorations, where dust presents similar challenges. 2. Interconnected nature of lunar and Mars exploration. The report underscores the interconnectedness of lunar and Martian exploration efforts. The technologies and knowledge gained from lunar missions are believed to inform future missions to Mars, particularly regarding regolith interaction and dust management. Significance. This interconnectedness suggests a strategic approach to space exploration where lessons learned from one mission can significantly enhance the efficiency and safety of subsequent missions. It highlights the importance of a sustainable exploration strategy that not only aims to return to the Moon but also sets the groundwork for humanity's future on Mars. 3. Safety as a priority in mission scheduling. The decision to adjust the timelines for Artemis 2 and 3 to prioritize astronaut safety is a critical point in the report. NASA administrators have cited the need to resolve technical challenges before crewed missions are launched, emphasizing the importance of a thorough testing phase. Significance. This commitment to safety reflects NASA's evolving approach to space exploration, prioritizing human life and operational integrity over aggressive timelines. Such an approach fosters public trust in space missions and may inspire future engineers and scientists by showcasing the importance of safety in pioneering endeavors. 4. Role of commercial partnerships. The report acknowledges the role of commercial partners such as SpaceX and Blue Origin in the Artemis program. These partnerships are crucial for developing the human landing system and next-generation spacesuits, which are integral to the success of the missions. Significance. The involvement of commercial entities highlights a shift in NASA's operational strategy, embracing public-private partnerships to leverage innovation and reduce costs. This trend can facilitate more rapid advancements in technology and expand the capabilities of space exploration. 5. Environmental Control and Life Support Systems (ECLSS). The report mentions the critical testing of the Environmental Control and Life Support Systems (ECLSS) on the Orion spacecraft during Artemis 2. This system is essential for maintaining a habitable environment for astronauts. Significance. ECLSS is a core component that determines the viability of long-duration space missions. Effective testing and validation of these systems are crucial for ensuring that astronauts can live and work safely on the Moon and subsequently Mars. The emphasis on ECLSS reflects a move towards sustainable human presence in space. 6. Cultural and historical impact of Artemis missions. The goal of landing the first woman and the first person of color on the lunar surface is a significant cultural milestone emphasized in the report. This aspect of the Artemis missions aims to inspire a new generation of scientists and engineers from diverse backgrounds. Significance. This focus on inclusivity is vital for fostering diversity in STEM fields. By highlighting the achievements of individuals from various backgrounds, NASA not only broadens participation in space exploration but also ensures that the future of space endeavors is reflective of a diverse society. 7. Holistic approach to lunar infrastructure development. The report mentions the Lunar Surface Innovation Initiative (LSII), which is actively engaged in developing systems for lunar infrastructure including dust mitigation, in situ resource utilization, and surface power. Significance. The holistic approach to developing lunar infrastructure is significant as it prepares for sustained human presence on the Moon. This strategy is not merely about visiting but about establishing a sustainable foothold which is essential for future explorations beyond the Moon, including Mars. 8. Gateway Lunar Space Station. The planned Artemis 4 mission aims to establish the Gateway Lunar Space Station. This component of the Artemis program is intended to serve as a hub for lunar operations and a stepping stone for deeper space exploration. Significance. The Gateway will play a crucial role in facilitating ongoing lunar missions and supporting future Mars missions. Its significance lies in its potential to serve as a logistical and operational base, enhancing NASA's capabilities in deep space exploration. Conclusion. The nuances in the report on NASA's 2025 moon landing mission reveal a comprehensive strategy that not only focuses on immediate goals but also prepares for long-term human exploration of Mars and beyond. By addressing challenges such as lunar dust, prioritizing safety, fostering commercial partnerships, and emphasizing diversity, NASA is laying the groundwork for a sustainable future in space exploration. These overlooked details are not mere footnotes. They are integral to understanding the complexities and ambitions of humanity's journey beyond Earth. 1. Technological innovations for lunar exploration. The Artemis program's focus on developing advanced technologies, particularly through the Blue Ghost Mission 1, highlights NASA's initiative to address the significant challenges posed by lunar regolith. The electrodynamic dust shield (EDS) and the stereo camera for lunar plume surface studies scalps represent critical advancements aimed at mitigating the risks associated with lunar dust. These technologies are not only essential for the success of current lunar missions but also have implications for future Mars exploration, underscoring the interconnected nature of NASA's endeavors. 2. Human-centric mission design and safety. The adjustments to the timelines for Artemis 2 and 3 reflect a strong commitment to astronaut safety in human spaceflight. NASA's prioritization of resolving technical challenges, such as issues with the Orion spacecraft's environmental control and life support systems, shows a methodical approach to mission planning that emphasizes safety above all else. This is especially pivotal as Artemis 2 will be the first crewed mission, setting a precedent for future crewed missions to the Moon and Mars. 3. International and commercial collaboration. The Artemis program exemplifies NASA's strategy of leveraging partnerships with international space agencies and commercial entities. The involvement of companies like SpaceX and Blue Origin in developing human landing systems and spacecraft underscores a collaborative approach to space exploration. This not only enhances technological capabilities but also promotes a shared vision for humanity's presence in space, highlighting the importance of global cooperation in achieving ambitious exploration goals. For long-term vision for sustained lunar and Mars exploration, NASA's Artemis campaign is designed not just for short-term lunar missions but aims to establish a sustainable human presence on the Moon as a stepping stone for future missions to Mars. The planned Gateway Lunar Space Station and the inclusion of diverse scientific objectives signify a comprehensive strategy to explore and utilize lunar resources. This long-term vision emphasizes the Moon's role as a critical platform for testing technologies and conducting research that will facilitate human exploration of Mars and beyond. 1. Apollo 11 Mission 1969. The Apollo 11 mission marked humanity's first successful manned moon landing on July 20, 1969. Astronauts Neil Armstrong and Buzz Aldrin became the first and second humans to walk on the lunar surface, while Michael Collins orbited the moon in the command module. The mission was a pivotal moment in the space race, demonstrating advanced engineering and technology. The Apollo program involved thousands of engineers, scientists, and support staff, showcasing the collaborative effort necessary for space exploration. 2. Mars Pathfinder 1997. Launched in December 1996, Mars Pathfinder was a landmark mission that landed the Sojourner rover on Mars in July 1997. This mission showcased innovative technology and engineering, enabling remote exploration of the Martian surface. The successful deployment of the rover involved extensive planning and collaboration among engineers and scientists. Mars Pathfinder helped pave the way for subsequent Mars missions, contributing significantly to our understanding of the planet and demonstrating the potential for robotic exploration. 3. International Space Station 1998 or present. The International Space Station ISS is a multinational collaborative project involving space agencies from the United States NASA, Russia Roscosmos, Europe ESA, Japan JAXA, and Canada's CSA. Since its first module launched in 1998, the ISS has served as a microgravity research laboratory and a base for scientific experiments. The construction and operation of the ISS required the expertise of thousands of engineers and scientists from around the world, showcasing the importance of international collaboration in advancing space exploration and scientific knowledge. The ISS has also been instrumental in preparing for future deep space missions, including those to the Moon and Mars. Future outlook, predictions for NASA's moon landing mission and beyond. NASA's Artemis program represents a pivotal chapter in human space exploration, with ambitious plans for lunar missions leading up to 2025 and beyond. As NASA gears up for its upcoming lunar missions, several key predictions can be made regarding the future of lunar exploration technology development and subsequent Mars missions. 1. Technological advancements in lunar exploration. The integration of over 1,500 engineers and scientists in the Artemis program will catalyze significant advancements in technology. The focus on critical technologies such as the electrodynamic dust shield (EDS) and the stereo camera for lunar plume surface studies, SCALPs, and missions like Blue Ghost Mission 1 will lead to enhanced capabilities for dust mitigation. These technologies will not only improve the safety and efficiency of lunar landings but also set the stage for more complex missions that involve human habitation and extended stays on the Moon. Prediction: by 2030, NASA will have developed a suite of advanced technologies that will allow for automated lunar operations, including dust-free landing zones, improved life support systems, and autonomous robotic systems for resource extraction and habitat construction. 2. Increased international collaboration. The Artemis program emphasizes the importance of global partnerships in space exploration. As NASA collaborates with international space agencies and private companies, the concept of shared missions and collective knowledge will strengthen. Countries such as Canada and nations within the European Space Agency (ESA) are already participating, and this collaborative spirit is expected to grow. Prediction: by 2028, international coalitions will be commonplace in lunar missions, leading to joint missions that leverage the strengths of each partner, resulting in shared resources, technology, and expertise. This collaborative framework will also help address global challenges such as climate change by promoting international scientific research conducted from lunar bases. 3. Establishment of sustainable lunar presence. With the Artemis 3 mission aiming to land humans at the lunar South Pole, a critical goal is to establish a sustainable human presence on the Moon. This involves not only landing astronauts but also building infrastructure such as habitats, scientific laboratories, and power generation systems. NASA's plans for Artemis 4 include the Gateway Lunar Space Station, which will support ongoing lunar operations. Prediction: By 2035, NASA will have established a permanent lunar base capable of supporting long-term human activities. This base will serve as a launch point for further exploration of the Moon, including resource mining and scientific research, as well as a staging area for missions to Mars. 4. Mars exploration as a direct outcome of lunar missions. The knowledge gained from lunar exploration will directly inform Mars missions. The lessons learned about dust mitigation, habitat construction, and life support systems on the Moon will be applicable to the challenges posed by the Martian environment. NASA aims to use the Moon as a proving ground for technologies and strategies that will be essential for Mars. Prediction: by 2030, NASA will finalize plans for crewed Mars missions utilizing data and technologies developed during the Artemis lunar missions. The first crewed mission to Mars is anticipated in the late 2030s, setting the stage for sustained human presence on the red planet. 5. A public engagement and inspiration. The Artemis program is expected to generate significant public interest and engagement in space exploration. Initiatives to involve educational institutions and communities in STEM, science, technology, engineering, and mathematics will foster a new generation of scientists and engineers. Prediction: by 2025, public engagement initiatives will lead to an increase in student enrollment in STEM fields by 25% in the U.S., inspired by the ongoing lunar missions and the potential for human life on Mars. Public-private partnerships will also flourish, with more companies engaging in space-related ventures. 6. Commercial opportunities in space. The Artemis program, particularly through its commercial lunar payload services (CLPS), will open up avenues for commercial enterprises to participate in lunar exploration. This includes launching payloads, developing technologies, and potentially mining lunar resources. Prediction: by 2030. A thriving commercial ecosystem will emerge in lunar exploration, with multiple private companies conducting missions to the Moon, potentially leading to lunar resource extraction and the development of space tourism. Conclusion: NASA's ambitious plans for lunar exploration through the Artemis program are not just about returning humans to the Moon, they are about laying the groundwork for a new era of space exploration that includes Mars and beyond. As technology advances, international collaborations strengthen, and public interest grows, the coming decade will be transformative for humanity's journey into the cosmos. The predictions outlined here, if realized, will mark a significant leap forward in our capabilities to explore, inhabit, and utilize other celestial bodies, ultimately redefining our place in the universe.